Hey guys, BuildZoid here, and today we're going to be taking a look at another B550 motherboard. This time it is the B550M Aorus Pro AX from Gigabyte. Now, this is kind of the Gigabyte kind of snuck this board out because they already have a B550M Aorus Pro, but that is actually a very, pretty different board from the B550M Aorus Pro AX that we're looking at here. From the name, you would think the only difference is that the Pro AX has a Wi-Fi 6 in the rear I/O, but actually, the bigger difference, at least in my opinion, is the fact that the Pro AX, and I can't really show it to you. Well, no, I can show it to you. This is a 6-layer board, which is why we can't see any memory traces on the top layer of this PCB. And so I requested a review sample of this board because I was really hoping that this would be like an MATX motherboard from Gigabyte that has the same memory overclocking capabilities that their 6-layer ATX motherboards have. It doesn't. So, yeah, it seems like it is a 6-layer PCB, but I guess this is some weird hybrid of the 4-layer and the 6-layer topology, because ultimately Gigabyte is actually using the same QVL for this board that they use for the 4-layer B550M Aorus Pro. So, you know, from Gigabyte's own testing internally, they just, you know, they're saying, yeah, this clocks memory the same as the 4-layer version. And my testing shows that it doesn't clock memory as well as the other 6-layer boards that I have from Gigabyte, like the B550 Master, or the B550 Vision, or the B550, or the X570S Master, for that matter. Yeah, which is a bit unfortunate, but it's not the end of the world, because this is still a pretty strong memory overclocker. So for 2x8 gigabyte, and I did all of my testing with Samsung 8 gigabit B die, and I also used the 5950X that I have. Now that 5950X is capable of over 4800 on 2x8 with, you know, good motherboards. On this board, it topped out at 4600. And I also tested 2x16, which so 2x16 is kind of awkward because you're not going up to these crazy high frequencies just in general, because 2 ranks of Samsung B die on each of the memory channels is just a bit much for the Ryzen memory controller. But it will do over 4000 no problem. And so I don't see, like, this is fine as far as I'm concerned, because that is more than your Infinity Fabric is likely to be able to sustain anyway. Because 2000 FCLK, for anybody who's tried it, just causes a flood of errors in Windows. So, yeah, and that doesn't change with this board, but at the same time, like, I was able to run at least benchmarks synchronized on 2x16 up to, like, well, over 4000. And then the same is actually true for 4x8, because yes, this is a daisy chain topology, but the Ryzen memory controller doesn't really seem to care very much. So also 4000 plus is possible. So in terms of memory overclocking, if you're doing a daily system, go for it. Like everything, like it does everything you need. In fact, it's a lot better than some of the other it's actually better than some of the 6-layer B550 motherboards out there from other manufacturers, like the B550 Strix XE, which I bought, and that board sucks, is the nice way to put it. That board, like, for comparison, the Strix, well, so, I guess, so, like, a B550 Master would do, like, 4800 plus for the 2x8 configuration, and then the 2x16 and 4x8 configuration actually behaves the same. So that's kind of interesting. But yeah, then, like, if you compare this to, like, say, a ASRock B550 Steel Legend, which is a 4-layer PCB, but ASRock is, like, insane. I have no idea what they did to their PCBs. That board will do, like, 4666 on 2x8, but actually struggles with 4x8 configurations as well as 2x16 configurations. So yeah, that's very interesting. That might also be down to BIOS tuning at that point, or Gigabyte's topology is just better suited to having a lot more load on the memory controller than whatever ASRock is doing. And so most of the differences come in on the the single rank high clock configurations rather than the low frequency stuff. But then we get to, say, the Asus B550 Strix XE that I have, and that board does 2x8 up to 4533, which is horrible as far as I'm concerned. And more importantly, it does 4x8 up to, like, 3866, which is, and the same is true for, like, 2x16, which is basically a massive disappointment in my opinion. So yeah, as far as, like, 6-layer, or actually just as far as B550 motherboards that I've tested memory overclocking on Go, this isn't the worst. Like, it's nowhere near the worst. For a daily system, this is more than enough in any direction. Like, if you want to run dual rank with over 4,000 megabits per second, you can. Like, that's not going to be any issues. And of course, if you use like lower load memory ICs like Micron or Hynix DJR, even higher speeds are possible. But I don't see much point testing those configurations because the performance doesn't like the thing is, like, yeah, you can get these insanely high clocks, but you're just going to get outperformed by a lower clocked, tighter time VDI configuration, so I don't know why we would want to talk about that. Anyway, so yeah, so the memory overclocking on this board is decent, right? Like, it's definitely not the worst board I've tested. It's also nowhere near, like, it's not on par with the ATX 6-star Gigabyte motherboards. And when it comes to memory overclocking, there is one frustration with this board, which is that there's no troubleshooting LEDs whatsoever. There's nothing. There's no postcode. There's not even like the 4 LEDs that you get on some boards to tell you what part of the boot up procedure you are in. You don't even get that. Now, that's not really a problem because as long as you don't punch in completely stupid settings, the board just kind of boots. Like, I literally took the settings I use on the B550 Master for 4x8 and I threw them on this and they just worked. So it's kind of like, yeah, as long as you're not, trying to push really high frequencies, it should be just fine, assuming that you also don't do anything stupid to your timings. And the auto recovery is okay. It's not the, well, actually the auto recovery on AMD motherboards just in general is not that great, in my experience. Yeah, so memory overclocking wise, like, for a daily build, I would not see any issues with this. So yeah, actually this does a better job of memory overclocking than the motherboard currently in my daily system. So yeah, because while it's not the best memory topology that Gigabyte has available right now, it's still a lot better than the initial release topology that they had for X570, which is what I currently have in my daily system. So anyway, yeah, we started with the memory overclocking because that's kind of the part of the board I was most interested in. So if you didn't care about that, well, now we get on to the rear I/O, which, as I mentioned earlier, you get Wi-Fi 6, 2.5 gig LAN. I believe that's from Realtek. Plenty of USB ports and Q Flash Plus, which allows you to update the BIOS of the motherboard without even having a compatible CPU for it or a CPU installed at all. So yeah, and this can also potentially help you if you brick your BIOS. So like you use the regular BIOS flashing method and the power goes out and the board doesn't want to boot anymore. Well, you could potentially recover from that kind of situation using the Q Flash Plus button. And if you want to use this board with an APU, you get a DisplayPort and an HDMI output in the rear I/O. Oh, and this little hole over here is for an LED to indicate that the Q Flash function is actually doing its thing. So it's kind of neat. And then, yeah, you get a bunch of USB 2.0 ports. I've not run into the USB glitching bug on this motherboard at all in my testing. But that doesn't mean it's fixed. That just means I didn't run into it. Actually, I've not run into that bug on any AM4 motherboards recently for a while, but I've still heard people complain about that. But like, it doesn't happen to me anymore. So as far as I'm concerned, it's fixed. Or at least seems to be mostly fixed. So yeah, it's kind of that for the rear I/O. And honestly, this is about as much rear I/O as at least I personally would need. So I consider this completely satisfactory and actually even good. Like, that's kind of like, the thing is, my main criteria is like, do I have enough USB Type A? And the answer on this motherboard is yes. I even comes with some extras for my uses. So yeah, I'm pretty pleased with this, with the rear I/O on this board. And now let's talk about the power delivery. So you get a single 8-pin power connector, which a lot of people might think, oh, you're not going to be able to max out your 5950X, except those people don't understand how much power a 5950X pulls. So let's put it this way. Gigabyte is actually using solid pins for this 8-pin power connector. All that really means is this is the high current variant of the 8-pin power connector, and that means this power connector can easily handle in excess of 300 watts. Your 5950X is going to be completely uncoolable long before you get to that level of power draw. So you don't really need to worry about that. So yeah, this is more than enough power for even a manually overclocked 5950X, which I don't really see why you'd even want to like do that. But hey, I'm not gonna stop you if you want to. I think like the thing is PBO will get you like 95% of the performance for like if you don't mess with the curve optimizer for like 0% effort. You don't need to put any work in. You just punch in a few, you just punch in a higher power limit, a higher TDC, and a higher EDC, and you're done. More multi-threaded performance. Like, yeah, if you want to, fiddle with it some more, you can. But even that, like, that's not going to make your power draw go up anyway. That's just going to reduce, like, actually, that's going to make your power draw go down. So, yeah, this is more than enough power connectors. Because you don't need the extra power connectors. The CPUs don't pull that much power. And for the VRM on this board, we are looking at a 5+2 phase, which, yeah, it seems like so 5+2 phase where we have a V-core over here, SoC over there. Our VRM controller is this chip over here, and this is that really obnoxious long part number of the RAA 2290004 from Renesas. Renesas owns Intersil, so that should give you some, like in the past we'd talk about Intersil controllers, now they're Renesas, so we talk about Renesas controllers. Anyway, 5+2 phase configuration, and yeah, this is a full digital controller, popular for anything from like, well, lower lower mid-range to high mid-range. Like, it's a perfectly good voltage controller. It's digital. It's got LLC. It doesn't do anything weird and stupid. So yeah, like this is a solid little voltage controller for a VRM on really any motherboard, and it's not really little. Like a little voltage controller would be like a 4-phase max, like 4+2 type deal. This is a 5+2. Like, you can build some seriously powerful VRMs with something like this. Actually, it'll even do 6+2. So, yeah, it's really not like a low-end controller that Gigabyte is using here. And then, of course, we do have 10 power stages here, which you can clearly see. And so what Gigabyte is doing for that is no more doublers. Doublers cost money. And also the benefits of, especially like what I find absolutely hilarious on modern motherboards is that there's so many modern motherboards that use ISL 6617s in synchronous mode, which admittedly, at least on paper, according to Intersil, the manufacturer of the ISL 6617, gives you slightly better efficiency than doing what this motherboard does, which is you take your PWM signal and you just sort of shove it into 2 power stages at the same time. Which is why this is a 5-phase and not a 10-phase, because there's no kind of interleaving. But the same is true for a 6617 running in synchronized mode. That doesn't give you any more phases. It just gives you slightly more efficiency, potentially. Yeah, like the thing is, this is a really cost-effective way of getting really high current handling capacity out of a VRM, and there's not really any major downsides to this. Like, you get the extra current handling capacity, you don't have to pay for ISL 6617s, and that's kind of it, really. This is the same thing that Asus has been doing on their motherboards for a very long time, though funnily enough, I'm pretty sure MSI was the first manufacturer to ever put power stages in parallel, because back in the X79 days, they wanted to build a 20-phase. One does not simply build a 20-phase back in the X79 days. But we will get to that board in a future video, hopefully, someday. I still need to do some testing with that board to make sure of some stuff, but yeah, anyway, so we're just running, parallel power stages here to get you 10 power stages for V-Core, and then the SoC VRM is not doing anything weird. You just have phases 1 and 2, whereas V-Core, you've got like 1, 2, 3, 4, 5. Now then, in terms of current handling capacity, we're looking at theoretical VRM efficiency, assuming 500 kilohertz switching frequency. Wait, I forgot to talk about the power stages. So the power stages that Gigabyte is using here are SiC 649s from Vishay Semiconductor. These are 50 amp components. I have no idea if they're DR. I think they're DR MOS. I say think because I can't actually find public datasheet for these chips, and so for the efficiency I'm relying on the datasheet of the 639, which is also a 50 amp part, and therefore should be basically the same, or at least that is my assumption. Anyway, yeah, it shouldn't really make too much of a difference. And I did do a practical test with a 5950X in a zero airflow environment. So we'll talk about that as well. 500 kilohertz switching frequency, 1 volt output voltage. Which I've not checked what switching frequency this runs at, but that doesn't really, like, with modern power stages, that doesn't tend to make as much of a difference as it would with, say, old power stages. 1 volt output voltage, because that's what the documentation is spec'd in, and that's kind of unfortunate. But with a 5950X, this is actually not too far off where the CPU ends up when you're pushing a lot of current into it, seriously. In Prime 95 with AVX, that chip pulls so much power, even at really low voltages. Anyway, so 100 amps output, this VRM should produce about 7 watts of heat, and that's only the power stages, not including inductors or power plane losses or any other losses, just the power stages. And basically, yeah, it'll handle a 5600X, no problem, 5800X, no problem, 5900X, which you'd be looking at more like 150 amps at that point, still no problem. That would only produce about 11 watts of heat on the power stages, and yeah, so the VRM will deal with that with no issues. Then 200 amps output, which now we're looking at like a manually overclocked 5950X, that'll produce about 18 watts of heat, and at this point you do start needing airflow because... well, you just sort of do start needing airflow over the heat sinks because, I mean, the heatsink has a lot of surface area, but at least horizontally, this fin stack orientation doesn't really work. That might be part of it, because I did actually test it just horizontally on a test bench. I didn't feel like putting too much effort into it. Like, my logic with VRM thermal testing is, like, if the VRM can handle no airflow on a horizontal test bench, then... it can handle any sort of more better configuration too. So, yeah. But yeah, like once you're really pushing a 5950X, you do want a bit of airflow over the VRM. But also, this board's not really designed for a 5950X, and I don't know that you should be building like an overclocked rendering station with your 5950X, because that's basically where this scenario applies, is like overclocked, constant heavy load, so basically a rendering workstation type deal. And also 5950X. None of the other chips is going to be able to pull this much power. So anyway, and also 200 amps going into a 5950X makes for a very, very hard to cool CPU. So yeah, you're not going to be cooling this level of current draw with an AIO. Like, you're just not going to cool that with an AIO. You're going to need like a custom loop or something. So yeah, I think at that point you should, well, I guess if you're doing like a custom loop MATX build, but like if you're doing that, you don't really have many better motherboard options either. Like, there's not really, like, I think all of the MSI MATX boards are also 4-layer PCBs, but different heatsink design approach, and the VRM wise though, I think they're basically the same. I've not had a chance to test them. I would assume that they run similar, like either similar temperatures, maybe slightly hotter due to the lower layer count, but yeah, ultimately, this, like, basically, if you're going to be hammering a 5950X, you can't just run it in, you can't run it in an airflow-starved hot box. That's all I'm really trying to say here. 300 amps output, this VR will produce about 36 watts of heat, and now we're talking about like LN2 overclocking territory, and the funny thing about LN2 overclocking is that it's generally not very sustained load, so, it took me, like, when I was doing the VRM thermal test on this board, it ran for like an hour, and that's because this heatsink has a lot of mass. It takes a while to get this to heat up. Actually, it takes close to an hour to get this to reach thermal equilibrium. So, yeah. Anyway, 400 amps output. This will produce about 60 watts of heat. And again, like, this is purely theoretical. And more to illustrate how, yes, these are 50 amp, nominally 50 amp DRMOS components, or at least I assume they're 50 DRMOS components. But you wouldn't even really want to run 40 amps through each of them at the same time, because the heat output would be completely uncoolable unless you were water cooling the VRM, which is like, why would you be doing that? Also, there's no CPU that you can put in this socket that'll pull 400 amps without destroying itself. So, good luck with that. Yeah. or more like without that much current flow destroying the CPU. So yeah, anyway, let's talk about the practical thermal test that I did. So I ran a 5950X in Prime 95 with small FFTs. So small FFTs, what was it? AVX, right, yeah, with AVX, and this ran for about an hour. I think it was like 49 minutes, but I also gave it like a warm-up period in the beginning because it didn't really... Like, I reset the temperature sensors so that I'd have a like average VRM temperature to look at the end of it. So we'll call it about an hour. And the VRM, so this is where we get to like the only issue I have with this board, which is the VRM temperature monitoring on this board. The board massively underreports the VRM temperature because Gigabyte, for some reason, put the temperature sensor over here. The hotspot is like here. Because of course it's over there. That's the middle of the vCore VRM. And the VRM temperature sensor, vCore VRM temperature sensor is over there. And I did check that. Like, that is actually the NTC resistor that is connected to our RAA 229004 for temperature monitoring. And yeah, it's just like here. And the thing is, that temperature sensor has two functions. One, it gives us a VRM temperature reading for things like over temperature protection and just, making sure, though technically you also have a thermal warning system from the power stages themselves, probably, I'm assuming. Again, no public documentation, but the vast majority of DRMOS components these days have thermal warning systems. So, it's not like we're only relying on that temperature sensor for for temperature limiting, but yeah, that is certainly a function that it can serve. And Gigabyte has used it like that on certain boards in the past. But the other purpose this serves is it actually is used for temperature compensating the DC current, like the DCR current sensing, which the controller uses to tell you how much current is coming out of the VRM. Because the way this controller monitors the current flow through the VRM is it actually uses the DC resistance of the inductors. Now, inductors are basically a fancy bit of copper wire encased in some magnet-like core material. And not necessarily, but in this case, like we have the casing on them. And anyway, so, and then also there's internally they're probably wrapped around some of the core material. The thing is, we'll not get into it. Like, I've seen inductors that are basically a strip of wire going through the core like this. And then you have also like fancier inductors where you have a coil and that then gets like smushed into a bunch of sintered material. And anyway, doesn't matter. The point is fancy copper wire with some fancy material surrounding it. Copper changes its resistance based on how warm, like what temperature it's at. So if your temperature compensation is over here and the hottest part of the VRM, well, like almost this entire section of the VRM is hotter than right there, which is true, you end up in an awkward situation where the current reading from the VRM is really inaccurate because the temperature compensation for the vast majority of the inductors making up the VRM is wrong. So yeah, as the VRM heats up, especially in a zero airflow environment, because if you have some airflow, the temperature equalizes across the VRM quite quickly. But with no airflow, the hotspot is over here, and the temperature difference between these two places can be as much as 16 degrees Celsius. At least it was in my testing. And that, I forgot to mention. And that was with a 330 watt power limit on the CPU and a 211 amp TDC and EDC, so current limit on the CPU. The end result of these settings was that before the temperature sensors, before the temperature compensation threw off the current readings, the CPU would be averaging around 180 amps of current draw, which, yeah, that makes sense for these settings in Prime 95. Incidentally, if you were actually optimizing your 5950X for, say, Cinebench performance, you would not use 211 amps of EDC or TDC. You'd use like 177, which would significantly reduce the Prime 95 power consumption. So yeah, like this really, like if you're optimizing your PBO settings for like gaming or just general lower thread count usage, like not totally hammering every millimeter of silicon inside the CPU with work, you wouldn't use such a high current TDC or EDC. But anyway, yeah, so with these PBO settings, there was like a 16 degrees Celsius temperature difference between right here and there. Over here, it was reading like 108 degrees Celsius, actually literally 108 degrees Celsius. And over here, we were getting 92. And for whatever reason, the VRM MOS sensor, which isn't the same sensor, which actually, I don't even know where that sensor is. I would assume it's that, because I had a really good hard look around the VRM to find another temperature sensor, and I couldn't find one. But there's like a temperature reading from the motherboard's Super I/O, and for whatever reason, that's even like a degree lower than the temperature reading from the VRM itself, which I'm not sure what's going on with that, but yeah, so Gigabyte kind of just shoved the temperature sensor in the wrong place. Now, as for the actual VRM temperatures of, 108C at the hotspot, this is in a zero airflow environment. It's with a 5950X getting absolutely railed by Prime 95. I have no issues with that part of the VRM getting to 108 degrees Celsius. I think that is a completely acceptable result, because it is. It's zero airflow, massive amount of power draw from the CPU. It took an hour for the VRM to get to that temperature and then sort of sit there. And this was admittedly in a 23, and this was with a 23 degrees Celsius ambient. Like, if you have any amount of airflow, the VRM very quickly drops below 90. And also, this was on a horizontal test bench, and I'd like to draw your attention to the design of this fin stack over here. In a horizontal orientation, this fin layout doesn't work because obviously, you get hot air that gets created in here. But if the heatsink is horizontal, that air has to rise that way. Yeah, that doesn't really work that great. So horizontal test bench for this style of heatsink is definitely not ideal because these fins are designed to be the hot air is supposed to rise in between those fins, right? It's supposed to rise up in between those fins. So this should be in a sort of standard case orientation. This should actually get even better temperatures. And that's still assuming you had no airflow. If you actually had somewhat decent case airflow, yeah, the VRM is never going to get up to 108 degrees Celsius. And for comparison, I've tested other B550 motherboards with similar VRM configurations with basically the same level of power draw. Though I think back then it was the 3950X, and it would, end up mainly I'm thinking of the B550 Steel Legend, and that would run basically at the same temperatures, if maybe a bit hotter, because that was a 4-layer PCB. So yeah, this sounds really high, but considering that most other people who test VRM temperatures on YouTube don't run their test until thermal equilibrium, which is what I do. I literally just wait for the temperature to stop rising. If it keeps rising, we keep going. If the motherboard eventually starts thermal throttling, that's when I say, okay, that's the end of the test. Or if the temperature gets so high that I'm uncomfortable with it, I also call that an end of the test, because I've had some motherboards that don't seem to have an over temperature protection, and I'm not really interested to find out if they shut down before the MOSFETs go thermal runaway or not. And usually I basically go up to 125. If the VRM keeps going above 125, that's when I call it end of test. But 108 in the test conditions that I ran, I think is a completely acceptable result. There are motherboards that would do a better job. Those motherboards cost significantly more, right? So, yeah, I don't really see this, I don't consider this a failure for this motherboard whatsoever, especially because I was really kind of abusing it with the way that I was testing it. So that's that. Now, one thing I do sort of want to point out, which is not really that important, but I find kind of interesting, and this is really what makes me suspect that maybe the memory section of this board isn't the same as the 6-layer topology that Gigabyte has on their ATX boards, and that is the fact that the VRM uses a very 4-layer style layout here. So here's the B550M Aorus Master, right, which doesn't have any 4-layer variant. The B550M Aorus Pro AX, to me, seems to be a B550M Aorus Pro, and then they slap 2 extra layers onto it. one at the top and one at the bottom. The B550 Aorus Master was always designed as a 6-layer board, and we can very clearly see sort of a typical 6-layer motherboard VRM design where we have this nice big V-core power plane. Then behind that we have this ground plane. And basically having these big fills behind the in the VRM section can help with thermals, because this will just act as a heatsink. Not a very good heatsink, but it will help with thermals a little bit. And again, this doesn't work in a horizontal orientation because the air is just going to get trapped under the board. So that's not really relevant to my test scenario, but still, maybe it would have helped a little bit. Also, you have, actually this 12 volt fill right here. So that's just the 12 volt power plane, and it goes all the way behind the power stages. And that could also potentially slightly help with the temperatures of the PCB. Just like more copper on the top layers, more better, especially if you have a lot of vias, which we do. Now, if we look at the B550M Aorus Pro, which is based on a 4-layer which I'm assuming is based on a 4-layer PCB, we don't see any of that, right? Like here we have our 12 volt power plane, which I guess actually reaches the power stages through an internal connection inside the PCB, because it's certainly not doing it on the back here. And I guess on the top layer as well. It obviously it reaches them on the top layer, but on the back we don't see this nice continuous 12 volt connection, which it's not really a problem. The VRM runs fine. It's just I find it kind of interesting that they, considering that they do have the extra layers, I'm surprised they didn't, take advantage of that. But I guess the idea was just slap together a Wi-Fi, a 6-layer Wi-Fi version of the existing B550M Aorus Pro. And so we have a lot of the leftovers from the 4-layer version. Also, the V-core islands, right? This over here where you don't have this one big continuous V-core power plane. Also, the B550 Master has the SoC that goes all the way to the CPU on the back of the board. We don't have that here. That big polymer capacitor in the socket is missing, because those are actually expensive. Even if they're made by APAC, they're still expensive. So yeah, I find that very interesting that we sort of have this, this is definitely a 6-layer PCB. We can see that very clearly from the memory topology, but it really looks like they just kind of slapped the extra layers on and then didn't really do much more with them than that. I assume the main reason that they even opted for a 6-layer version of the board was to get that M.2 slot in the rear I/O, or that mini PCIe, whatever. I think it's an M.2 slot, a vertical one though. Anyway, this add-in card, I'm assuming the extra traces that they needed to run to get that connection over there, that's why we have 6 layers. Maybe they added some more rear I/O as well. I didn't really check the 4-layer board for comparison. But yeah, you don't really see very clear, this is a 6, it's not the VRM area basically looks very 4-layer PCB. The memory area looks very 6-layer, but doesn't clock like the 6-layer. So, interesting sort of, interesting example of a motherboard where you don't have, it has 6 layers, but, it doesn't match other 6-layer designs, even from the same manufacturer. So, I wanted to point this out because, sometimes people, because as much as I do point out, hey, this board has a 6-layer PCB, 8-layer PCB, just because the layers are there doesn't necessarily mean that they are being used to the, maximum of their benefit. Ultimately, the board still runs fine. I just find it kind of interesting that we do have this still very, this really looks like a 4-layer PCB over here. So, yeah, I just kind of find that interesting. That they didn't really do much with the extra layers, but then again, it it'll run a 5950X just fine, and so I don't really see a reason that they needed to redesign it massively. So yeah, though I do really wish they added some troubleshooting LEDs. That would have been a really nice addition. So that's kind of it for the B550M Aorus Pro AX. Not to be mistaken with the regular B550M Aorus Pro. I'm not sure how much this is going to cost. I've not been able to find it at any stores. Actually, wait, no, I did forget to mention one thing. Actually, wait a minute. So these are Nichicons, because we have FP5K. Oh, I guess APAC ran out of capacitors. So now we have These really look like Nippon Chemicons to me, but I am not 100% certain about that. I have no idea who that makes these. Like, these give me, like, these really remind me of the capacitors that I've seen on, like, MSI boards, but yeah, I have no idea. These are 8-pack. Oh boy, yeah, they're really running out of components, I guess. I have 6.3 volt 8-pack 5,000 hour rated caps over there. No idea who makes those. Nichicon for those. That's a Japanese manufacturer. But on a board this low end, I wouldn't expect to see Nichicons at all. I would have expected more APAC in the rear, like in the high voltage side. And then over here we have no idea. There's an APAC over there. Yeah, a real mishmash of capacitor brands. Component shortage, yo. Because the norm for a motherboard like this from Gigabyte, at least before we started having all of these, like, there's not enough of literally anything, was that you would just have APAC capacitors for everything on a motherboard of this tier. You would have them on the high voltage side, the low voltage side, just everywhere. And here we have them for, like, the USB ports and the RGB, maybe? I'm not even sure what this one's for. But yeah, we have one hanging out over there. So that's super interesting. Because I was like, oh yeah, and then the board uses APAC polymer capacitors. And it's like, actually, well, yes, but not really. I'm not sure who the other, like, I don't know who that third manufacturer is. If you do recognize these capacitor markings and you know who makes those, it would be much appreciated if you'd leave a comment with that. Though I'll try look it up now that I've actually noticed that I have no idea who makes those. Or I'll just ask Gigabyte, though. The issue is they might actually just be switching them based on whatever's available the day they make the board. And to be fair, the differences between various polymers aren't going to be... Like, solid polymer capacitors are generally really robust, so I'm not too fussed about them changing the manufacturer of those. Like, if these were liquid electrolyte capacitors, then which manufacturer they're using would be a lot more concerning, but as it is, it's just like, they're solid polymers. They don't tend to go you can't really go too wrong with those as far as I'm aware. So yeah, anyway, that is actually it for the Gigabyte B550M Aorus Pro AX, a, you know, solid little MATX motherboard from Gigabyte. I'm not sure that it's necessarily the best B550M ATX motherboard, but at least in Gigabyte's lineup it should be, because it's the only 6-layer MATX motherboard that they make. And yeah, I'm not sure that there's not that many 6-layer MATX boards. And, you know, I did point out how the VRM still looks very 4-layer, but that doesn't change the fact that there's probably like the power plane internally is significantly beefed up compared to a 4-layer PCB. So yeah, anyway, that's it for the video. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch. Both Patreon and Teespring help out immensely with running the channel, so it would be much appreciated if you'd check them out. And yeah, that's it for this video. So thank you for watching, and goodbye.